Victoriya on the PyIRI. It's a mouthful, but
Hi, everyone. So in terms of the place of PyIRI and JEDI, as Dave said, we've done some work to populate SEMI3 model with the PyIRI results, so it can be publicly available and that JEDI can work with SEMI3. I'll give you kind of overview of how PyIRI was developed. And what was the motivation behind it. So these four are kind of like my babies, called babies. And PyIRI was developed for the data assimilation model for the ionosphere. It calls Anchor. So David and I, we are from the different groups at NRL, and I'm from ionosphere group, where we have kind of a separate data assimilation scheme, which calls Anchor. So when I started developing Anchor, my goal was to have some sort of background which can be obtained very fast, especially because, usually data assimilation uses standard grid, right? You have just one geographic grid for all time frames. We're trying something different with Anchor, which is for each time frame, we have different grid in terms of longitude and latitude locations because we're working in magnetic field grid. So that left me with a problem that for each 15-minute time window, I had to produce a new background at totally different locations. And for the grid, which is like 1,500 points, it took me forever to get any background. And that was the main motivation of producing some climatological model that can be run really, really fast. And just since I have a stage, I can advertise other things, which can be very useful. They're all community code on GitHub. Plus, you can just do pip install things like PyIRTAM, which is kind of an extension of PyIRI code. And very soon we will release PyRay, which will be the first HF ray tracing code for the community, also fully in Python. All right, so PyIRI. Everyone talked a lot about the ionosphere today. It has pretty complex structure. It has some distinguished horizontal structure where the position of those density enhancements are determined pretty much from the sun's position, right, where your solar pressure and solar radiation is to ionize stuff in the atmosphere. Plus, it has a particular vertical structure where we have this F2 peak, which is the main, the peak of the ionospheric density, and everything below it, pretty much in modeling sense, can be a function of this position and density in the F2 region. So the climatological models such as IRI analyzed a lot of data to produce coefficients that determine how in terms of horizontal structure, the peak density is distributed around the world and how the height of this peak is distributed. And those two parameters, the NMF2, the peak of the F2 region, and HMF2, the height of this peak, that's what drives the IRI model. And everything else in IRI model are pretty much a function of those two parameters. So IRI model was developed in the late 1960s. Those are the two main papers that describe it. So the main authors are Johnson-Gallet and Johnson-Graham. What they did is they analyzed a bunch of ionozone data. So they extracted the NMF2 and HMF2 parameters from ionozone data. Then, and since ionizon is such an instrument, its location is fixed, right? So they can look at the time series of those parameters. So they found monthly mean values for each ionizon. Then they found coefficients for the functions that can describe the diurnal variation. For example, here the dots are the mean monthly values, and a certain coefficients will give this the lines through those points. Then they combined all of the ionizons to find coefficients for spherical harmonic functions to describe the horizontal distribution of the parameters. And as a result of their work, we have those so-called CCIR coefficients, and another set of coefficients is ERSI coefficients. Those are 12 files, 12 because 12 months, and they're very, very ugly files. First of all, if you just open it first time, you would have no idea even how to read it, unless you know exact Fortran code, like the how would you call it? Like yeah, a special line of Fortran code of how do you interpret those that seems like columns of data. But anyways, in this file, if you open one of those files, you'll have 2,858 coefficients, and they can be logically, after some work, split into an array of 13 by 76 by 2. Plus there will be another set of those numbers which correspond for the M3000, or it's the same as HMF2. So anyways, let's try to focus on this first array. So 13 means those coefficients for the diurnal functions, and 76 is coefficients for global functions, and 2 is just the minimum and maximum level of solar activity. So if you think about it, PyIRI is so simple that it has only 2 points for your F10.7, and everything else is just a linear interpolation between those 2 points. I think that's a major weakness for the current climatological and spheric modeling, and that thing needs to be addressed in the future. This is how those 13 functions look like. They're just simple Fourier series, so sum of sines and cosines. And these are the global functions, and they're not just spherical harmonic functions. They're some sort of hybrid of spherical harmonics. They're just combination of sines and cosines, and the variables are the longitude, latitude, and the dipole. What's the name of it? I've forgotten. So basically the angle that describes modified deep angle, yeah, that's the name. So that's how the modified deep angle looks on the map. So that's a variable that gives this magnetic dependency. Anyways, those functions are quite hard to model because it's hard to put those things in a loop to produce those functions. But yeah, that's another future work for ionospheric modeling community to come up with a set of functions that don't require writing them by hand, at least. So that's just an examples of how those functions look like. So again, it's pretty similar to spherical harmonics. All right, classical PyIRI code. How did it do the work? So for a position of longitude, latitude, and time step, it would calculate this modified deep angle. Then it would open this CCIR coefficient files, do the work, close CCIR coefficient files, calculate your NMF2 or HMF2. If you need to do the next time step or the next position on your globe, you'll have to repeat this process again. And so rinse and repeat, rinse, repeat. But the funny part is that the CCIR file, this huge table, actually contains information about 24 hours and about the whole global distribution of this NMF2. So why do we actually have to do it separately for each time and for each location? So this is how PyIRI was born. We start with a global array of positions. Then we calculate modified deep angle for this global array. And then we calculate all of those ugly geographical functions using this information. Then we start with array of UTs, how many, whatever time resolution you're interested in for your simulation. And then we calculate those sines and cosines, or diurnal functions. Then only once we open this CCIR file, we form the matrix, and then the whole process is just a multiplication of 3 matrices. And this multiplications, the single multiplication, gives you the electron, not electron density, but NMF2, so the peak of your density for the entire day, for the entire globe. A little bit more information of how this is done. Again, we can express our diurnal functions in terms of a matrix. We'll have 13 functions and 76, the coefficients, the matrix that contains coefficients is 13 by 76. So we form another array that contains those diurnal functions that will be the size of your time resolution and the 13. Then we'll do the same for the spherical harmonics array. As a result, it will have 76 elements, and then Ng is number of your grids that you use in your horizontal plane. And then the multiplication essentially gives you this movie which represents the NMF2 for the entire day. And this process takes only a couple of seconds. Well, of course, depends on your horizontal and time resolution, but 3 seconds is kind of average time. And just to kind of give you a perspective of how slow it used to be, or how slow the classical Fortran IRI code is, to produce the same movie, I would need to execute Fortran code 6 million times. And if to use a standard kind of public Fortran code, that would translate to 900 hours. So 900 hours in comparison to 3 seconds, it's kind of a big deal. PyIRI is well compared to IRI code. There is a slight difference between the formalism that we decided to use. For example, IRI code expresses the thickness of the bottom side region in terms of 2 parameters, B0 and B1. In PyIRI, we decided to keep just 1 parameter, kind of the thickness of the Epstein function. But other than that, everything else looks pretty much the same. If you're interested to learn more, there's a paper about it, and the code is publicly available on GitHub, and it's PyPy installable. So if you say pip install PyIRI, it will be all yours. And it has a good documentation with different examples and so on. How am I doing on time? Do I have more? A little bit. Okay, cool. So again, how you can use PyIRI for DA applications? Well, it's a very fast way to produce your background, and you can play with it. You can create an ensemble of how many ensemble members you would like, and it will be very fast. PyIRTAM is another thing. It's kind of an extension of PyIRI. So PyIRTAM is a data simulation model. So Ivan Galkin is the main guy there. It uses the data from a big ionizon base called Gyro, and it assimilates the parameters from those ionizons to update the CCIR coefficients. So how does it work? So the same kind of going from the same principle of how IRI coefficients are being defined. They start with this, with the set of coefficient as an initial conditions, and then depending on the data, they correct the coefficients itself, the time series of those coefficients. So essentially for each 15 minutes, they have a new set of the same CCIR coefficients. skip that. All good, but they need to rely on the same scheme as IRI did. So, and we're like, well, let's expand PyIRI to help them to do this process faster. And that's what has been done. How can you use PyIRTime? PyIRTime is a great tool for validation. I think Dave uses this to validate his results of data assimilation. So you either need to have license to have the PyIRTime coefficients, or if you're interested in like 24-hour-old coefficients, they are publicly available. And PyIRTime has an inbuilt tool that helps you to download these coefficients. Also, you can construct your covariance matrix by using PyIRTime results, because they are much better than your regular climatological model, because it already has kind of like the DA-driven thing in it. Yeah, I think that's all I had. Thank you so much, and fine, you know where to find me.
Okay, I think in the interest of getting to lunch, we should postpone questions until the discussion section afterwards. But thank you very much, Victoria. And with that, I'll turn it over to we and the organizers to get us over to lunch.
Since we are running late, I would like to cut our lunch a little bit shorter. And I hope we can come back around 2:05, 5 minutes after 2, give you a little bit of time to settle down. Yeah, it does close at 1:30, so we need to grab our lunch there, but then you can sit there or walking back.